Hello and welcome, everyone. My name is Selena Smith. I'm with Westinghouse Women Pittsburgh chapter, and welcome to our demonstration with Penn State of the Breazeale reactor. I'm really glad that you've joined us. First, I want to mention that we are recording this meeting. So if you do not want to be recorded, you can either, well, be aware of your surroundings. So if you don't want the background to be shown, you can use an effect in the background, or you can turn off your screen if your camera if you don't want to be recorded. And if you don't want to be audio recorded, there is the chat function that you can use if you have questions. There's the chat, and there's also a Q&A, and we'll be monitoring those throughout the meeting. So feel free to ask questions. In addition, I have a recommendation so that you can get the best viewing experience possible. We have highlighted the two screens. And so if you make sure that your screen is in gallery mode, you'll be able to see both of the screens that we're going to highlight during the webinar today. I'm happy to have my colleague, Kelly Ann Zayan, here to help me moderate. And I'm happy to have Zach Van Horn from Penn State's Radiation Science and Engineering Center with me today too. He's going to lead the demonstration. So Zach, do you want to take it over?
Absolutely. So thank you very much, Lena and Kellyanne. I'm Zach. I'm from Penn State University. I work here at the Breazeale Nuclear Reactor at the Radiation Science and Engineering Center. The Breazeale Nuclear Reactor is the oldest licensed operating nuclear reactor in the United States. So that means that all of the reactors that came before us were either military or government use. Our license was given in 1955, so we're coming pretty close to our 70th anniversary here in a year or two. Behind me, I have Katie Baker, who is one of our undergraduate reactor operator interns as a junior in nuclear engineering. She joined the team as an intern over the course of about 10 months, would you say, Katie? Yeah, 10 months. In addition to taking classes, she went through our training program, took a 3-part exam with the Nuclear Regulatory Commission to get her license to operate the reactor for you today. So without further ado, I'm going to switch over to the console view. So now you should be seeing what Katie is seeing there on the screen. And on the left screen, on the right side of the left screen, somewhere in the middle, you can see that there are a few different indications of where our control rods are right now. There she is pointing it out. We're at a position, what we call standby. In standby, the amount of neutrons that are being generated by nuclear fissions inside the reactor are roughly double that of when the reactor is entirely shut down. That is, all of the control rods are completely lowered into the core. The top portions of those control rods on the screen you see are made of boron. Boron is a neutron absorbing material, so when they are lined up with the fuel, they shut down the reactions by absorbing neutrons. As we take the control rods, as we take the boron portion out of the reactor, we increase the reactivity. That is, we can increase the power by allowing those neutrons to interact with fuel, uranium atoms, rather than the boron inside of the control rods. So I'm going to ask Katie now. Katie, can you please start the reactor, bring it to 100 watts, use automatic mode, and use a 15-second period, please.
So for the one, 100 watts with a 15-second period?
That's correct.
All right. So I already found my positions where I'm going to bring the rods up to. I'm going to get this number to approximately 921, give or take a little bit more. And then I'm going to use these 3 rods to achieve criticality. And then once I get to critical, I'm going to switch into the automatic mode, and the computer's basically going to take over for me until I get to that endpoint of 100 watts.
Right.
So, all right. The reactor's being started.
So a few things as we go on that Katie mentioned that I'll clarify. What it means when the reactor is critical or gone critical is that for every reaction, for every fission of a uranium atom, there's one more that follows it. So it isn't the kind of bad thing that you would imagine from a standpoint of the reactor being in a critical condition or on the edge of being very dangerous. Critical really just means that it's at a balance at a point where if we gave it a little more push, it would go up in power, or if we pulled back just a little more, it would just go down in power, but not very quickly. So as you see here, Katie is pulling out those control rods one by one, starting with the transient rod. The transient rod is the one on the far left. It's followed by air as opposed to more fuel, which is why on the screen you can see that it is blue underneath. The other three rods, what we call the safety, the shim, and the reg rods, are all followed by fuel. So as you take the control rods out of the core, you also introduce more uranium into the core. And as she takes those control rods out, you can see here at the bottom, we have a measure of what we call reactivity. And that reactivity is in dollars and cents. That is a normalized unit that is antiquated from the Manhattan Project. Interesting story behind that is when the Manhattan Project scientists and engineers were starting up the first of the nuclear reactors or doing their research into the atomic bombs, they measured the reactivity in dollars and cents, which is really just a fraction of a type of neutrons in the core, delayed neutrons. And when they communicated that across the United States to different portions, they did so in dollars and cents so that their communications would look like budgets. They would just be a lot of ups and downs and taking away dollars, taking away cents. And if anyone were to intercept those communications, they wouldn't look very important, or at least they wouldn't be traced back to the things that they were actually doing. So here we've added about $2 of reactivity to the core, and over on the right side here, you see those lines are starting to move up. These lines each indicate, they're all the same indication, and they are measuring the number of neutrons that are hitting a detector close to the reactor core. The number of neutrons in the core is directly correlated with the amount of thermal output that the core is giving off. So it's the amount of neutrons that are interacting with uranium atoms and causing fissions. Each fission gives off about 2.5 neutrons and also about 200 million electron volts of energy. So those two things can be correlated, and our detectors are calibrated to give us not just the number of neutrons, but actually the thermal power based on that. All three of those indications are in log scale. So there are moving what seemingly is like an X equals Y type graph type increase, but it's actually more of a Y equals E to the X type graph. It's an exponential increase that we've taken the log of to make it look a little bit easier for the operator to understand. And then as the top line goes out of view, the bottom lines will come in. Switching on. Okay, so now that Katie has found that the reactor core is critical, which means that without moving any rods, we still see that the neutron population is increasing. She's going to switch it into automatic mode to take the reactor to about 100 watts in a 15-second period, which is pretty quick. And what we're going to see here is that the safety, the shim, and the reg will be drawn out by the computer. You can see they're coming out here now to bring the reactor supercritical with a fairly quick period. So over here on the right screen, you can see the moment she entered automatic mode is where that dip and then subsequent increase in neutron population is. that neutron population is associated with pulling the control rods out of the core. So right now they're all sitting at about 9.5 inches, except for the transient rod. And then when we hit 100 watts, instead of being supercritical, the reactor will need to decrease the reactivity to bring the power back to criticality or steady state. Just about there.
Operating at 100 watts.
So here at 100 watts, you see that the rods are being pushed back into the core from 9.5 inches down to about 9.3 and probably end up somewhere around 9.2, 9.3 inches out of the core. And over here on the right screen, the power and the neutron population has leveled off. So the reactor is critical now because for every reaction, for every fission that occurs, one more reaction happens after that. And over the course of any given time scale, the same amount of thermal power and the same amount of neutrons will be interacting. So to get from supercritical down to criticality, the rods had to plunge back into the core to stop the increase of power. The next thing I'm going to ask Katie to do is to increase power from 100 watts to 500 kilowatts using manual mode, please.
Just wait 5 minutes to take that position.
Oh, sure.
I'm gonna figure out where they're gonna go.
So I'm going to zoom out here and tell you, show you kind of what you're going to see. Here at the Breazeale reactor, we have a trigger type reactor. Trigger type reactors have been around since the 1950s. Our reactor core, although our facility had been here since 1955, the reactor core that we have here today has only been installed since 1965. We had a entirely different type of reactor from 1955 to 1965. The trigger type reactors mostly have these buttons here. 500 kilowatts, yes. There are 3 rows of buttons. And for each of the 3 rows, there are 5 buttons, 1 for each of the control rods. And then, as you can see on the console, a row for a spare. The middle row of buttons is the up buttons. So each of these buttons will take the control rod out. The bottom row of buttons are the down buttons. They will push the control rods into the core. And then the top row of buttons that are red and covered with this piece of plastic here are what we call the scram buttons. The scram buttons will cut power to each of the control rods, and it will drop the control rods into the core via gravity. Right now, 3 of the control rods, the safety, the shim, and the reg, are each being held up using electromagnets. Those electromagnets are energized, and we know from the console they're energized because of the yellow top of each control rod. And then the transient rod is held up using air pressure. So I'm not sure if you can hear it over the Teams chat, but there's a hiss coming from the reactor bay right now, and that hiss is the air pressure that's holding up the transient. By pressing the scram button on that rod, it will close a solenoid valve and allow the air pressure, or take away the air pressure, dropping that rod back into the core. If something were to happen where the reactor operator wasn't comfortable with what was going on, if she believed that there was some sort of safety that was being some part of our safety program that was being compromised, she could hit that big red button at any given time, and we would drop all the control rods back in the core, reducing power from about 100% to about 2% instantaneously, just by lining up that boron with reactor fuel. Okay. So,
Okay, I'll start.
So when Katie starts to pull out these control rods, what you're going to notice is that the rods will start to come out of the core. But unlike what happened with the initial startup to 100 watts, the fuel temperature, which you see in the box in about the center of the screen, right now is about roughly the same as the pull temperature you see at the bottom of the screen. As the control rods come out even farther and we increase the power, the thermal output of the reactor fuel, the fuel rods are going to start to heat up, and that fuel temperature is going to deviate from the pull temperature. The hotter the fuel temperature gets, the more it wants to push the power back down. So you can imagine a cart on a hill. If that hill is getting steeper and steeper on its way up, you need to give the cart more and more power. You need to push it with more energy to get it farther up the hill. That's sort of what's happening here is that we're pushing a cart up the hill, and the hill is getting steeper with the fuel temperature getting greater. And to make up for that, Katie has to put her foot farther down on the gas to get us to the next power level. So we'll watch here as she goes up from 100 watts to 500 kilowatts. She'll do so in manual mode, and you'll watch as she presses those buttons to get us up to the next power level.
If you want to 500 kilowatts, maybe.
Yes, please. 500 kilowatts in manual.
The reactor's operating at 100 watts and power is being increased.
And as you start that, I will step out for a second to turn the reactor core lights off. Those of you on the call should notice now that the reactor core lights are off. What will happen as we get closer to power is that a blue glow will start coming from the reactor core. That blue glow is what we call shrink-off radiation. Shrink-off radiation is caused by the particles moving around in the reactor, moving faster than the speed of light in water. Now, we can move faster than the speed of light in water because the speed of light in water is about 75% of that of the speed of light in a vacuum. So we're still obeying all the laws of nature. Einstein hasn't pulled us over and given us a speeding ticket quite yet. So when that happens, you get something very similar to a sonic boom, only with light waves instead of sound waves. And the shock wave effect that gives off just happens to be in the visible spectrum. So we'll start to see that as we increase the reactor power. Back over to the console. You see now that we're just passing about a kilowatt of thermal output. Over here on the right screen, the linear mode power is starting to kick in. And you can see the exponential curve of that graph. So we'll switch over to a higher level graph here so you can see the power coming past 10 kilowatts rather. And just a few moments ago, the fuel temperature was about 18, 19 degrees C, and you can see that it's starting to increase at this moment. Without moving any of the control rods, the power is increasing at a pretty good pace. So there's the power increasing, and the control rods are still right about where they were, except for the transient rod a few moments ago. What's going to happen here soon is that fuel temperature is going to start to increase, which you see that here. We're up to about 25 degrees Celsius. And that increase in fuel temperature is pushing back on the reactor power. If you hear those clicks coming from the console, that's Katie kicking up each of those control rods to make up for that increase in fuel temperature. So here we are just passing 50 kilowatts now, increasing power exponentially, and we're just passing 45 degrees Celsius on the fuel temperature as well. Katie has a lot of experience bringing the reactor to power in manual mode. She had to do so during her exam to prove to the examiner that she understood the physics that was going on in the core and knew how to respond accordingly.
16 punches.
We just passed 200 kilowatts and we just passed 100 degrees of temperature. We're just, this is where, yeah, so as we go up in power, the temperature starts to increase a lot faster and you have to click the buttons even faster yet to get to the next power. So here we are at about 400 kilowatts, and you can see Katie's having a little bit of a hard time keeping that exponential increase going. So now she's working against that fuel temperature increase. And this is something we call a negative temperature coefficient. That is, the higher in power we get to, the more the reactor, the fuel itself, the materials of the fuel push back on us. So to get to the next step, Katie has to bring those control rods out even faster.
Seriously, undershot trains.
So one of the issues that you might just have heard her say is that she had undershot the transient rod. That is, that she prepositioned the transient rod a little bit lower than what is needed to get to 500 kilowatts. And one of the reasons that might have been is because yesterday we did some operations late in the day, and that created what we call xenon poisoning. When the uranium atom splits open, it splits into a number of different elements, but one of the elements that it splits into that we're concerned about is iodine. Iodine will decay by beta emission, radioactive decay, into xenon 135. Xenon 135 acts sort of like a boron atom, sort of like a control rod.
Reactor's operating at 500 kilowatts.
The more xenon that's in the core, the more reactivity we have to give it to get to the same power level. So even though we've reached 500 kilowatts now, because that fuel temperature is still coming up, you can hear that Katie is still pulling out those control rods just to maintain 500 kilowatts.
Is there a fuel temperature that correlates with 500 kilowatts, or like, is it always the same temperature, or does that change?
Yeah, so it's about the same temperature every time when we go to 500 kilowatts right here. At about, I think it'll even out right around 340, 350 degrees Celsius. That is being measured from the center of a fuel rod that's located as close to the center of the core as we can get it. So that's pretty much the hottest spot of the core. You'll notice now in the core video that the reactor at power is glowing that bright blue strike-off glow. And whenever you feel comfortable, Katie, you can put it in automatic mode and level out at 500 kilowatts.
At this facility, oh, I'm sorry.
No, sorry, yeah.
I was gonna say, at this facility, where's the power going that you're generating right now?
Yeah, so all of the heat that is being generated, it just goes into the water that is inside of the tank that holds the reactor core. So the reactor itself is not that big, even though it's hard to get a good measure of it from the video. It's even hard to get a good measure of it in person because it's under about 20 feet of water. The entire tank is under, it's 24 feet deep, and it's about 20 feet to the top of the core. And it's roughly 2.5 feet or so in width. So Just big enough that you could probably fit on your kitchen table at home, or, swim down there and give a big hug. I wouldn't recommend it. Please don't do that. But it's not that big. The tank itself, because it's so deep, holds about 71,000 gallons of water. So you can imagine trying to bring a stock pot of water up to a boil to boil your pasta for dinner or something, but trying to do that with a candle. So the candle gets really hot and our core gets really hot, but it doesn't get hot enough to bring all of that water to boiling temperatures.
Okay.
So the warm water around the core rises to the surface and cool water sweeps in underneath.
I have another question in the Q&A here.
Yeah, please.
You mentioned water temperature as a reactivity coefficient. What are some other coefficients that affect reactivity?
Well, that's a good question. So the reactivity is, we mostly control reactivity with the position of the control rods. So the more boron we put in the core, the lower the reactivity is. And we balance that with how much boron is either in or away from the fuel. Then, of course, as we talked about, the temperature also pushes back down the reactivity. And then we talked very briefly about something called xenon poisoning, or any other sorts of poisoning, which are other materials that could be generated in the core from either fission or from an experiment, which will absorb neutrons. The entire reaction is dependent on how many neutrons are available to cause fission. So anything that takes away those neutrons is going to decrease the reactivity, and anything that puts more neutrons into the core is going to increase that reactivity. And the way the temperature does that is pretty interesting, in fact. Attached to our fuel is a material called zirconium pine. And Katie, whenever you are prepared, please shut down the reactor and set up for a $2 pulse, please.
Understood. Shut down the reactor and set up for $2 pulse.
Yes, please. So while Brady does that, I am going to share my screen.
Looks good. We can see your presentation.
Excellent, thank you.
You're welcome.
So this is the fission process. Whenever a neutron interacts with the uranium atom, it causes fission. It gives off
The reactor's operating at 500 kilowatts and it's being shut down.
about 2 or 3 neutrons, and also some more 2 or 3 neutrons, and also about 200 mega electron volts. You capture those neutrons. We put a control rod into the core. The control rod absorbs the neutrons, and if you balance it just right, you get this 1-to-1 ratio, which for every reaction, there's another reaction, and we call that criticality. This is a 1/3 scale model of our reactor core, and it's kind of hard to tell here just how big the fuel rods are. But here on the right side, you can see just kind of where they're located, and then on the left side, and also in the video, you can kind of make out how those work out. This is Scout, Katie, and Jake. Scout, Katie, and Jake are holding fuel rods. You can get a better glimpse of just how big one of those fuel rods are. With the interns there holding them. So they're roughly 24 inches long each and about 1 inch in diameter. At a power reactor, you're going to see much thinner rods so that you can get the heat from the fuel into the water. Here, because we don't care much about doing that, we don't produce any electricity here, and we don't want to, or we don't care to boil the water. Our rods are a little bit thicker. They're made of that, not just the uranium metal, which serves as fuel, but also zirconium hydride, which serves as what we call the moderator. The moderator is a material that slows neutrons down. So neutrons, in order to cause fission, need to slow down to about the same speed as the other atoms around it. When they get released from the fission reaction, they move very quickly, and they can't do that. So to stop that reaction, or to stop them from moving so quickly, we put hydrogen atoms in the way. Hydrogen atoms are about the same size as the neutron. So as the neutrons slide into those hydrogen atoms in the zirconium hydride, they lose a lot of energy, sort of like billiard balls, and slow down. The slower the neutrons are, the more likely it is for them to cause fission. If you've ever been mini golfing, you can think of pulling out a driver from your bag at a mini golf and hitting it very hard. And the odds of you making the hole are very, very low if you hit the ball too fast. Whereas if you use something like your friends as a backboard and hit the ball into them, that ball's going to lose a lot of energy and stop right where you, at least, right where you hope the hole will be. Here we use the hydrogen atom and the zirconium instead. Now, because the hydrogen atoms in our reactor are actually built into our fuel rather than at a power reactor, those hydrogen atoms are built into the coolant around it. The temperature of the hydrogen is dependent on how much power the reactor is giving off. So as the temperature of the reactor increases, so does the temperature of the fuel and the moderator. And as the temperature of the moderator increases, it pushes the spectrum of neutron energy higher so that they don't cause more fission. That's all to come around and say that the reason why the negative temperature coefficient exists because the moderator doesn't take away neutrons, but it doesn't slow them down enough to cause another set of fissions. I hope I answered that question to the extent that it deserved.
How often do you have to refuel, or do you have to refuel at all?
Yeah, so our reactor, the core has been here since about 1965, and about half of the fuel rods that are in the core today are the same fuel rods that went into the core in 1965. So they are original to the trigger core that we see here. We don't have to refuel very often. We don't use our reactor the same way a power reactor does, where it will go up to full power, and the rods will be there anywhere from 4 to 6 years, producing full power all the time. We're here 9 to 5, Monday through Friday, and we start the reactor up to when we need the neutrons from it to do our experiments, and we shut it down when we don't need it anymore. And Friday afternoon, we can lock up the building and all go watch Penn State play whoever they're playing on Saturday afternoon. Very good. Are there other questions in the chat that I can answer while we're waiting on Katie?
There's
Zach,
none.
I have a question.
Oh,
So
yeah, please.
I think I read in the news that you're going to be adding more of the these like tunnel systems to do more experiments. Can you talk to that?
Yeah, absolutely. So pull up this slide here.
I guess they're called pneumatic tubes. Is that it?
So the tubes I think you're referring to are our neutron beam ports. So on the screen now, I know there's a lot going on here on the screen, but what I want to point out is that this is the picture of the core at what we call the D2O tank. This is a tank that's full of heavy water. The heavy water is there so that we can use more neutrons in our neutron beam. And then here is a 3D model of that system. The neutrons that come out of the front of the core are what we use to do our experimentation. So about 1 × 10⁻13 neutrons come out of the core every second and every centimeter squared. That's a lot of neutrons coming out of the core all at once. They will run into those heavy water molecules and get scattered, and they'll bounce around, sort of like ping pong or what am I thinking? Pinball machine. All those neutrons will head down one of those beam ports that you see here, one of these 5 arms. And just the ones that happen to make it down the tubes are what we use for our experimentation. So here in beam port 4 on the far right, or far left rather, we use something called neutron radiography. Neutron radiography is using the neutrons to take pictures of different things. Now, neutrons travel through things a little bit differently than X-rays do. Most people, I imagine, understand that when you go and get an X-ray done, what you're looking for is to get those X-rays through soft material like skin and flesh and see very heavy material on the inside, something like the calcium in your bones or perhaps metal. The things that we're looking for are things that are metal, and we're looking for light elements on the inside. So what you're looking at here is the hydrogen fuel cell that we did some research on about 15, 20 years ago. So the hydrogen fuel cell is a steel box with 2 gas inlets for hydrogen and oxygen. As hydrogen and oxygen come together to form water molecules, they will release an electron. At one point, we thought those electrons would be enough to power our vehicles. So we did some research into this, and to understand how this thing worked, we wanted to understand how water flowed through. But if you look at an X-ray of this, all you can see is a black box. Wouldn't be able to see past the steel on the outside. But taking a neutron radiograph is a lot different. Those neutrons will travel through the steel, through the iron, as if it wasn't there at all, and then they'll get stopped by the hydrogen atoms inside of those water molecules. So what you're seeing on the right picture here is a false colored photograph of the water molecules. It's the shadow of the water molecules that show through. The red portion of it is more densely packed water molecules, more densely packed hydrogen, where the blue section is less densely packed. And what you'll notice here in the center on the right is that there's a lot of water that is building up around these corners. And what the researchers were able to find with this particular experiment is that water was being pushed back through the channels rather than continuing on the path to get through the cell. And that backflow reduced the efficiency of the fuel cells. And with this data, the researchers were able to go back and redesign the channels to make the fuel cell just a little more efficient. Another thing that you probably heard about, and I'm sorry that I took a long way around to get to your question, is this beam port that's second from the right, the larger one called the cold neutron beam port. That cold neutron beam port is going to cool neutrons from thermal levels down to about 20 Kelvin, really close to absolute zero. And at those incredibly low energies, we can direct neutrons from the reactor, from the cold neutron source into different experimental facilities. And the newest one that will be here any day now is something we call the SANS, a small angular neutron scatter. With that piece of machinery, we will be able to take measurements at the moment that the neutrons impact our target nuclei. And that opens up a whole new section of research that we are incapable of doing now, that we will be capable of doing here very soon. This piece of equipment is being donated by a lab in Germany, just outside of Berlin. They didn't need it anymore, so they essentially put it on Facebook Marketplace and said, "Hey, whoever wants this piece of equipment, we don't need it. Come pick it up." We were the first ones to raise our hands, so they are donating it to our facility to use for the foreseeable future. That will show up here in the back, about I think 5 or 8 different shipping containers. So it's a big piece of equipment, and they'll send it to us with probably 1 Allen wrench and a set of Swedish instructions. Over the next year, we'll hire a dozen or so interns to put it together piece by piece. Are there other questions that I can answer?
I have another question, Zach.
Yes, please.
You said that there's heavy water in, I think you were saying it's in a portion of the reactor, not the whole pool, right?
That's correct. So
Okay.
the heavy water or deuterium D2O is inside of this horseshoe-shaped tank. So this tank is like a half moon with a cutout in the middle of it that's just the shape of the reactor. The heavy water we use inside of that tank is so that we can get our neutrons from the reactor core into the neutron beam lab. If we were to fill that with normal water, light water, H2O, that hydrogen would capture a lot of those neutrons, and we wouldn't get the flux that we need for.
The reactor's operating at 100 watts.
So just inside of that tank is where those neutron experiments will go. And then I know you noted that you mentioned the pneumatic transport, so I will point those out as well. Here on the screen, there are 2 tubes that are coming out of the top of the D2O tank off to the left. One of those tubes is carrying high pressure gas. We use carbon dioxide rather than air because air has element argon in it that can become very radioactive. So we use CO2 instead. That gas pressure can take neutrons or take samples from our neutron lab into the reactor, to the D2O tank to be exposed to the neutrons in the reactor. And then using the gas pressure, we can pull those out and back into the lab very quickly so that we can analyze the very short lived isotopes that come from those experiments. One of the examples, I'll back up just a few, is in an experiment we did in the late 2000s, where we got a number of tree ring samples from Cornell University. Cornell University has what's called the dendrochronology lab. As you guys probably know, when you cut down a tree, you can count how many rings there are to know how old the tree was when you cut it down. They took it a step farther. They told us what years those tree rings were formed, and also they compared it to building materials like in homes and buildings, and then even all the way back to Roman era ships but going back 2,000 years, we know we have samples of tree rings that can be dated to those particular years. And then when you shoot it with neutrons, perhaps there's something like gold inside of it, where gold 197 becomes gold 198. Gold 198 will release a gamma ray and also a beta particle to become mercury 198. And that gamma ray that comes off of it is always 411,000 electron volts. And because it's always 411,000 electron volts, we can detect the gamma rays that come off of that to create this spectrum that have very high, very narrow peaks. Each of those narrow peaks corresponds to another isotope. So here at 411.8 kilo electron volts is the peak that corresponds to gold 198. And we found that in some years, those trees took up a lot of gold, where in years just around it, the trees didn't take up much gold at all. And the working theory now is that during those years, or just previous to those years, a volcano had erupted somewhere nearby, putting sulfur into the atmosphere that rained down as acid rain and made the gold a little bit more soluble for those trees to then take up during those years. So here on the screen now, you see that we have shut back down to about 100 watts. Katie is lined up with the safety, the shim, and the reg in position critical at 100 watts. So we're at that 1-to-1-to-1 ratio of criticality. And the transient rod is left all the way into the core. There's also a stopper on the transient rod that right now is pulled out to about 10 inches or so. So what we're going to do next is a demonstration of just how powerful or just how much that negative temperature coefficient, that negative temperature feedback feeds into our reactor. So we're going to, in a moment here, count down 5, 4, 3, 2, 1, and then use the air pressure to move about 10 inches of boron out of the core as fast as we possibly can. Removing all of that boron at once is going to dramatically increase the reactivity of the core. And with all of that boron moving out, we go from that 1-to-1-to-1-to-1 ratio of criticality suddenly to 1 to 2 to 4 to 8 to 16, an exponential increase on the factor of picoseconds. And in roughly 1/10 of a second, what you're going to see is the reactor change power from 100 watts of where it is now up to about 400 million watts. And that will happen in about 1/10 of a second. At the peak of that transient, the greatest number of neutrons will be in the core, but they will all be moving too fast to cause fission because the reactor fuel is heating up so fast, it pushes the power back down, and the fuel coefficient, the temperature coefficient, actually overcomes the reactivity and stops the reactions from happening. So, Katie, you're about ready to
I'm gonna double check everything.
okay. So here we'll give it in about 10-20 seconds. Katie will give us a countdown, 5, 4, 3, 2, 1. You'll notice the large spike in power here on the screen, but also on the core screen, there'll be a quick flash of blue light, that strike-off light. I promise that I don't have a camera flash, in the core that I am shooting off. The flash of blue light that you will see will be actually be generated by the power transient that the reactor core is going. All right, so Katie's ready. He'll give you a countdown.
Good. Good. The reactor is operating at 100 watts and will be pulsed in 5, 4, 3, 2, 1.
There it is.
I don't know
Over
about
here.
everybody else, but I was really excited by.
The countdown
was
helps.
cool.
So there you see on the right screen here the number of neutrons. At the moment that we pulse, it goes straight up and off the screen. And then over here to Katie's left is the indication of power. The entire bottom of that green graph, that is a half a second long. Of course, where it says 0, it's about 100 watts, and then the power is linear in megawatts. So it looks like we peaked right under 400 megawatts. And then on the right screen where it's red, that is the fuel temperature. So that's actually lengthened out to about a minute. The fuel temperature increases from the outside of the fuel rods in, so we don't pick it up in our thermocouples that are located in the center of the fuel, so it takes a little bit longer to kick in, but we know that the fuel had to heat up, because if it didn't heat up, the power would still be going up now, and we would be having a very bad day here. Very good. So that is the coolest thing that I can show you legally. And we have done, I'll check our board now. We have done since 1965, 9,313 times. So near the beginning, in the early days, you used to do that just to understand what was going on. Nowadays, we have a pretty good idea of how it works, and we do it just to show off. So thank you for being here and giving us someone to show off to.
Thank you for showing off.
Absolutely, we love it.
We have another
Switch back.
question that just came in. This is from Shauna. How many university reactors are in the US? And why is Penn State's the best?
We have about 15 other reactors that are similar to ours, where we can go to about, we're licensed to go to 1 megawatt. Other reactors like MIT is licensed to 6 megawatts. Missouri is licensed to 10 megawatts, and they produce a lot of the nation's medical isotopes there. There are another 15 to 20 reactors outside of those that are at university campuses, more so to do educational activities rather than research activities. So we do, so our research here pretty much can boil down to put things in front of the reactor to hit them with those neutrons. And we do that for a lot of different research groups here at Penn State and at other universities, and also companies like Westinghouse, who need to test their material before they put it into much bigger reactors than what we have here. So to answer your question, there's roughly 30 or 35 reactors at university campuses across the country. And Penn State's is the best because of the people, certainly, that we have here. Katie decided to come to Penn State for a reason. People like her, Jesse, who's on the call, Zach, who's on the call as well. The people that I work with every day, I couldn't imagine being anywhere else. Very good. Anything?
That's terrific.
Anything further? I had a great time. I don't know if anyone can raise their hand and unmute their videos or anything, but I'd like to thank Selena and Kellyanne for joining us today and partnering with us to bring you this webinar.
Yeah, thank you, Zach. It was wonderful.
Yes.
If we'll stay on for a few more minutes in case people have questions. But before you hang up, if you are thinking about doing that, please put in the chat. If you are watching with other people as a group, please put in the chat how many people are with you.
There are a lot of you guys from the Pittsburgh area. If you have, it's hard to come by transportation budgets now, but if you have the ability to come see us at Penn State, we have a program to bring K-12 students through the facility and do much more in-depth hands-on work than we were able to do over the phone today. Please get a hold of me and we can set something up.
Yeah, Zach, you know what I will do is I will put my email in the chat. And if anyone would like to work with Penn State and work with Zach to arrange a field trip or a visit, then I will put you in contact if I can't do two things at once. All right.
Thank you, Scott.
Yeah.
Excellent. That's great. Wonderful. So any of you guys in classes right now have questions for Jesse, Zach, or Katie? They're all undergraduate students here at the university now. Maybe you have something just general about coming to Penn State, or any other school. Going into the nuclear field. I'm sure Selena and Kellyanne would love to talk to you about it. anything at all. It doesn't just need to be directed to me.
I have a question for, I think it's Katie, or really when you do the, you're licensed now to, or you passed your qualifier to be a operator here, does that mean you will be able to be fast tracked as a reactor operator at a power plant, or, what do you intend to do with that? And what can you do
So-
with it?
Yeah, oh, microphone. Can you hear me?
Yes.
Okay, so, my plan is, so now I have my reactor operator license. Next step I can go up to senior reactor operator, but I'm not gonna plan on doing that here. My plan is to graduate here in May, I believe. I'm not sure when graduation is, if it's May
May
or
or
June.
June, yeah,
Yeah,
one of them.
one of those months. And then I'm probably gonna be staying here for an additional year to get my master's degree. And then after that, I've been actually looking into potentially being a naval nuclear engineer and being in the Navy for about 5 years. And then after that, I would probably go for my SRO at like a power reactor.
Okay, cool, thank you, thanks for sharing.
Yeah, that sounds amazing.
Yeah, I'm excited. Hopefully I can get the Navy to pay for my master's. So
Yeah.
that's gonna be
Absolutely.
it'll be a nice 26K dent in my. If not, I have to start saving now. Any other questions for me?
There's nothing in the chat right now.
Yeah, I think that's it. Shauna, what was that you said, Shauna? I can give you
Here.
See,
tea in naval reactors. All right, well, I think we can wrap it up if we don't have any more questions or anything in the chat.
Nothing in
So-
the chat.
Yep.
thank you
I
all
just-
again so much.
Yeah,
Yeah.
thank you so much, Zach and Katie and everyone who was helping us. I thoroughly enjoyed this, so thank you so much.
All right. Until next time.
All right, see ya. Thanks.